Hello, AP Calculus students. Mr. Ford here. We're looking at 750 and 751. These are the last two problems we're going to do from 715. Our last section on the related rates topic, by the way. But these problems are not related rates. 750, we want to use the first and second derivatives to determine the following locations for f of x equals x times e to the x. First, we're going to find the relative minima and maxima. This is going to happen at any time when f prime of x is equal to 0 or if it's undefined. That's where we're going to find those spots. We'll be able to tell if they're positive or negative, or maximums or minimums, depending on what the positive and negative are. In fact, we'll probably end up doing a and b together, because increasing and decreasing has to do with whether f prime of x is positive or f prime of x is negative. So let's go over here into the space and let's do a little bit of work here. We got our original function, f of x, which is x times e to the x. And we are going to consider the derivative of this, f prime of x. And for this, we're going to need the product rule. The product rule is going to have the original first thing, which is x, times the derivative of the second thing, which is e to the x, plus the original second thing, e to the x, times the derivative of the first thing, which in this case is 1. I'm just going to put that down there as a placeholder and then clean it up in my next step. So our derivative here, f prime of x, is equal to x times e to the x plus e to the x. Now we want to know, if we're going to talk about maximums, relative maxima, or minima, we need to know places where this equals 0. So the next phase is, okay, when does 0 equal x times e to the x plus e to the x? A really good way to answer this question would be to factor out e to the x. We could subtract e to the x over, and that brings up some suggestions, but we never want to cancel out a variable that we're trying to solve for. So the best way to solve this problem would be to factor out e to the x, which would leave us with x plus 1, like this. And I like this because now we have two things multiplied together who equals 0. And this means that we kind of have two cases. Either e to the x equals 0 or x plus 1 equals 0. And this is true. Let's see. This one here on the left, this is never true. You can never raise e to a power and get 0. And this one over here only happens at x equals negative 1. Right there. So there are no places where this is undefined. And the only places where the derivative is 0 is at negative 1. So we should just kind of, let's think about a sign chart for this problem, because if we think about our f prime of x on a number line, we really are concerned about what's happening at negative 1. Let's think about what's going on before that and what's going on after that. And you could just choose a number like negative 2 and plug it in. Or you could just consider what's going on. If you plug in negative 2, and I'm plugging negative 2 into f prime of x. If I plug in negative 2, I like to plug it in here, honestly, in my head. Negative 2 plus 1 would be negative 1. And e to the negative second power is always positive. So that's a negative times a positive, and this is negative over here. If you plug in 0, really good answer over here, plug in 0, e to the 0 power is 1, 0 plus 1 is 1, so it's positive over there. So I think a safe answer for A then, because A is asking us, make a list maybe down here. A is asking us for any relative minima or maxima. I think there is a relative minimum at x equals negative 1. And I know that because f prime of x changes from negative to positive at that point. Question B is asking us for where it's increasing and decreasing. We can answer that question right now too. F of x, the original function, is increasing on the range from negative 1 to infinity because f prime of x is greater than 0 on that range. And the opposite is also true. F of x is decreasing on the domain from negative infinity to negative 1. Again, because the derivative here, f prime of x, is less than 0 on that range. So we see that by kind of just taking the derivative and then considering where the derivative is positive and where the derivative is negative. Question C is going to ask us for any inflection points. That's going to happen at f double prime of x changing sign. We're looking for where the second derivative changes sign. So let's shift gears a little bit. We have our derivative. Let's use this version of the derivative right here. Let's think about our second derivative. Let's bring it down here. Let's just kind of work on this. F double prime of x in this case. Well, you know, the cool thing is that we already know what the derivative of e, or x times e to the x is. It's this whole expression. So as far as the first term goes, the derivative of x e to the x, we already kind of know that's going to be x e to the x plus e to the x, because that was the derivative last time we did it. Of course, we have to also consider the derivative of e to the x, which is e to the x. Now you can clean this up a little bit. F double prime of x equals, well, yeah, honestly, you could factor in e to the x out again. And this would be x plus 2. I'm kind of in my head doing kind of a mini step there. I'm combining together these guys into 2e to the x right there, and then factoring the 2 out. Like that. Now, if you think about where this changes sign, you know, it might be helpful once again to think about when this equals 0. And it's going to change sign, I guess. Well, I don't know if it changes sign there, but it definitely is going to equal 0 at x equals negative 2. Is where it's going to be 0. So the question now is going to be, does it change sign there? And I believe that it does. If you consider f double prime on a number line, kind of like we did before, this time we're going at negative 2. You know, the thing is, if you plug in any number less than negative 2 there, you'll get a negative number times a positive number, and that's negative here, and then positive. So I believe there is an inflection point for question C at x equals negative 2. F of x has an inflection point at x equals negative 2 because f double prime of x changes sign. And then question D, intervals over which it's concave up and concave down. We've also answered that question here too, because we kind of already have it here. F of x is concave down on negative infinity to negative 2. And then we know f of x is concave up on negative 2 to infinity, because we already have these negative and positive ranges for that right there. Let's take a look at the graph really quick just to kind of get an idea that we're right here. X times e to the x. X times e to the x power. I'm going to graph that on the old standard window here. Yeah, it does kind of change concavity. Oh, you can't. Hang on. It's too blurry. Let's see if I can fix this a little bit. Yeah. You know, you can kind of see it's very hard to see, but there is a concavity shift right there at x equals 2. There's also a minimum here at negative 1, and then it bottoms out and increases again. So we are correct in our analysis, which is a cool thing to be. Let's look at one more question here. We'll look at 51. The point from problem 719 that travels along the x-axis, so that its time t at position is given by that function. We want to calculate the average velocity of this point. At which point during the interval was the point traveling at its average velocity? Well, here's this thing. The average velocity, this is a position function. So we're going to need to use the slope version of this, the mean version of this. So what we need is s of 5 minus s of 0 over 5 minus 0. This actually won't be too tough to do. I noticed right away that if you plug in 0, all those t's become 0. So this is going to be really just s of 5 over 5. So S of 5 on my calculator, that is going to be 5 to the third power minus 5 times 5 squared, which is also 5 to the third power, plus 4 times 5. Didn't need a calculator for that. That's 20. And so this is 20 over 5, and that's 4. The average velocity is 4 feet, or units per second, I guess. Oh, there's units on this one. It's on the x-axis, so there's no units. Of course, the next question is, at what point during the interval does that point travel that average velocity? So what the mean value theorem guarantees is that there is some spot where s prime of x is equal to 4. That's the thing. The instantaneous rate of change has to match the average rate of change. So our s prime of x in this case is 3x squared. I guess I'm substituting x for t. It doesn't matter. Minus 10x plus 4. We want to know when that equals 4. If we subtract the 4 from both sides, we get 3x squared minus 10x equals 0. We can now factor the x out and get 3x minus 10 equals 0. We can use that zero product property from before. This happens at x equals 0, which is, that seems kind of weird that it's happening at 0. But then it also happens at 10 over 3, which is about 3.3 repeating. Those are the two places where you actually get that same velocity happening. Pretty cool. Well, there you have it. I'll publish these videos, and you can use them to help you out. We are finishing 715. On Monday, I'm going to give you a take-home quiz for the rest of this, and you'll be able to finish that up, and we're going to move boldly forth into Chapter 7. All right, I'll see you in the next video. You guys are awesome.